All right, so just to give you a little visualization of what's happening, if you turn to your textbook, page 408, this is if we had this shape revolved around the x-axis. This is a little visualization of what it would look like. This pink image here is a disc or a slice cut out of the 3D object, and so again you can see the radius here, half the diameter, is from the x-axis up to that point of the curve. So that's a little visualization of what's happening, and now we can revolve solids around the y-axis instead of the x-axis. So here we have an example bounded by the horizontal line y equals 1, the graph of natural log of x as shown in the figure. What is the volume of the solid generated when region R is revolved around the y-axis? So by the way, they could use rotation or revolve. So if you imagine taking this and rotating it around the y-axis, sorry, I believe earlier I said x-axis, y-axis, you would have something like this. So imagine it like a very strange shaped bowl, I suppose, that has a flat bottom of the bowl. However, I should say bowls are hollow. This one is not hollow. This is a solid rotation. So if you imagine this is a slice, let's pull it out here. Now our slices are horizontal instead of being vertical. So here we are still going to use the same formula. We still need to find the volume of the slice of this disc. Again, the center of this disc out to the edge is the radius, and the center this time is now the y-axis instead of the x-axis. And again, the height will be however thick this disc is. So here, my thickness of this disc, my height, is dy this time. Again, I have horizontal slices instead of vertical slices, vertical rotations like last video. And so we still have this radius here being from y to this curve. So this curve is y equals natural log of x, and we need it now in solved for x. So we need it in terms of y, since our slices are horizontal. So just a little refresher, natural log is the same thing as log base e of x. And so some of you may have learned it as, in order to solve for x, some sort of arrow. I'm guessing you maybe learned it like this. If you had me for Algebra 2, I taught it as base answer exponent. So this means e to the y is equal to x. So that is actually solved for x. That's all it took, was just switching it from its log form into its exponential form. So this is the radius. This is how long our disk is here. It is e to the y long. We're going to use the same formula, except now instead of respect to x, it is respect to y. So our limits are going to be based on the y values, not based on the x values. Okay, so my x values actually go out a little bit further, but consistently my y values are going from 0 to 1. And then here is my radius, e to the y squared, and again my thickness is dy. So similar to last time, e to the y squared is the same thing as e to the 2y. And very similar to one of the last problems, we're going to use U-substitution. And again, I don't have a 2 anywhere to substitute in, so I'm going to divide by 2 on both sides. And we have to put in a 1/2 somewhere. So my 2y becomes a u. My boundaries are from 0 to 1. However, when I plug them in to substitute in for u, 2 times 0 would still be 0. But this time 2 times 1 becomes 2. So it does change my upper boundary. The antiderivative of e to the u is e to the u from 0 to 2. So e to the 0 is 1, and at this point you'll notice choice letter B is the R option, except they just extended the 2 to divide all of it, which we could do. We could put this over 1, and 2 times 1 would be 2. All right, again, go ahead, pause this video, try example 5 on your own. When you click play, I will go over it. So this region is bounded by the x and y axes, the horizontal line y equals x, and the graph of y equals square root of x minus 1 as shown in the figure. What is the volume of the solid generated when region R is revolved around the y-axis? So again, I'm going to go ahead and draw a picture as best I can of what's happening. So we are rotating around the y-axis. And so if I were to draw a horizontal slice here, we have, again, the radius going from the center out to the disc. So it's going from the y-axis out to the curve. And again, my height would be however thick this slice is, so it's dy, again, because it is with respect to y, we have horizontal slices. So in order to find how long this radius is, we do need to solve this equation for x. So go ahead and add 1 to both sides. And to undo a square root, we square both sides. So x is y plus 1 squared, so that is my radius. And we're going to use the same formula. Again, be careful on your boundaries. This should be the boundaries on the y-axis, so it's going up from 0 to 1. My radius is y plus 1 squared. And remember that the radius needs to be squared, so square your radius. And my thickness of my slice is dy. Y plus 1 squared is y plus 1 to the 4th. And so here you can use U-Substitution. If you let u equal y plus 1, we have du equals dy, and that works out well. We have a dy right there. So this turns into u to the 4th du, and my limits, if I plug in 0 here, 0 plus 1 becomes 1, so instead of 0, I now have a 1. If I plug in my upper limit here, 1 plus 1 becomes 2. The antiderivative of u to the 4th is u to the 5th. Divided by 5, and I'll go ahead and plug in those limits from 1 to 2. All right, so if you go ahead and work all that math out, you will get letter B, 32 pi over 5. All right, that's that video, so go ahead, check for your homework online, and again, remember I'm holding those conference calls on Schoology. You can see the dates, they're posted on Schoology.